Oke, Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Thanks for joining with us, PT Berca, in webinar session. This morning webinar session with topic material measurement and in bioengineering and healthcare research. This webinar will directly delivered by Keysight expert this morning. Let me introduce myself. My name is Gusti Hermawan from PT Berca, and I am as host for today's webinar. This morning we have Mr. Sai Pomakeson. He is the senior product marketing application specialist at Keysight, and then he based in US, California, and also we have Daniel Yap as Asia Pacific Education and Research Business Development Manager at Keysight Technology. Also, we have Chin Kiat Chua. For today's webinar, the agenda is we will have presentation about the topic from Sai Pomakeson about the material measurement in bioengineering and healthcare research. And then after that, we will have Q&A and also the discussion regarding the topic. And the last one is we have closing. Okay, to shorten the time, I will pass the presenter control to Sai. Is it direct to Sai? Okay, Daniel.
Yes, directly
Okay,
for Sai. Yeah.
okay, to share the material. And then, okay, Sai, I will
Okay.
leave it to you, the presenter.
Okay.
Okay.
Okay. I'm going to share my screen. Let me make this bigger. Can you see my screen? Okay.
Yes, yes.
Okay. So welcome to material measurement webinar, and this is focused on bioengineering and healthcare. Even though I have many other topics, so as I go along, please feel free to stop me and ask questions as I go along. So this is a live presentation, so feel free to stop me anytime. With that, let's get started. If my voice doesn't come clear enough, also someone please let me know so I can make some adjustment. So here's the outline. So first I will talk about some definitions and market trend, and then go over let me get the laser pointer. Go over all system and the available solution that we have today. And then I'll go over some of the measurement methods and perhaps give you some strengths and limitation. And then since this is focused on bioengineering and healthcare, so I've focused more specifically on this area here, and I have a little bit more details. And then to wrap up with some research area that's currently going on and some of the solution available to this research area. And then we can stop at the end for questions and answer, or as I mentioned, feel free to stop me and ask questions anytime. And again, thank you for attending this webinar. So definition, there are many definitions like loss tangent, dissipation factor, DF, DK, permeability, dielectric constant, permittivity. There are many terms that you may come across, and many times they just meaning the same thing. However, they have different ways of saying that. It depends on some people's preference. So with that, let's look at some of the basics. So permittivity, also called dielectric constant, which is described how material interact with electric field, which is represented by the K letter or equal to absolute permittivity or the permittivity related to free space. It consists of two components, one called real part of the permittivity and another one called imaginary part of permittivity. So also called DK as well. The same as permeability measurement, exactly the same, except that this portion is using to measure magnetic properties of material that interact with magnetic. So how it interact with magnetic field is exactly the same as electric field, except this is more magnetic materials. Most of materials are non-magnetic, so most of the research and material used in industries are non-magnetic. This permittivity is complex value, but also called a dielectric constant, which is sometimes cause additional confusion. So as mentioned, the material interact with the electric field or magnetic field. Two things can happen. So one we call a real part of permittivities, which is measure how energy storage from the electric or magnetic field. Another one called a loss, which is imaginary part, which measure how much energy lost or dissipated based on the material that is used. Another term that you come across is called loss tension or called dissipation factor. So this is one term that's used to describe the relationship between the real part and imaginary part of permittivity. When the relative permittivity draw in vector sum and using the real part and imaginary part, they are 90 degrees out of phase or opposite. So if you remember very background math, so this is called tangent angle, which is where the tangent delta come from, is also equal to 1 over the Q factor. Some people call it tan delta, loss tangent, dissipation factor, or DF, all meaning the same thing. Another interesting term is called relaxation constant. This is used in many applications, especially for liquid and chemistry. This is used to describe how the polar material interact with the electric field. So in this case here, the imaginary part is low and the real part is high at start off. As the frequency increase, the imaginary part increase and the real part decrease, where the maximum loss or maximum heat dissipation occur at the relaxation time. So this is where the molecule cannot keep up with the frequency rotation, or sometimes is used in these Debye equation for that to figure out when that material is back to original state when the field is removed from materials. Some of these terms you may be familiar already, just in case you're not. This is a quick review. So when it comes to actual materials, there are basically two major type of materials. One called isotropic and another one called anisotropic. So this is a difference, especially when we come to actual measurement. And this may not pertain to bioengineering or healthcare. However, this is a parameter critical that most of material people need to be aware. For example, here, supply A measure permittivity in plane direction. It come out to be 4.3. And measure in thickness direction, like this here, come out to be 4.2. And when you see in our data sheet, it says nominal value. In this case, it measure in plane direction, so it gives you 4.3. Okay? And supply B measure the same material in the plane direction came out to be 4.55, which is close to 4.3, which is reasonable. However, if you look at the thickness direction, it's a big difference, 4.22 versus 4.02. So why is it difference? So the answer is we give you at the end. So in the meantime, you want to think about it as I go through my presentation. So this is where market trend. We see that aerospace defense, a lot of communication move up high frequency, excuse me, as well as in the 5G area, because most electronics, cell phone, now moving to 5G, 6G, automotive, and in your case, a majority of you probably in the biomedical or bioengineering and healthcare and food. So these are the area that many research people do, like yourself. So I'll quickly go over some of the automotive radar. So as you know, in front and the back of the car, there are some radars. So in the front, long range radar using this frequency range, really high frequency in millimeter wave, and the rear side using lower frequency. Okay, so and then we move up and higher, so because we require more data processing. So 1 gigs, 60 gigahertz band. So that equivalent of using this area, if you download movie 120 minutes, roughly take you 10 seconds. Imagine that. Some of the millimeter material material require bumper, antenna, radome requirements. Basically, you want some material in front of bumper or anything that you want to be transparency, like nothing happen, low cost, and some of the electric loss material sample relative to the free space is at 3.0. This is the decay value or permittivity value. All these applications require low permittivity and low loss. So with that, go to some of the measurement methods and strengths and limitation. Again, if you have any questions, please feel free to ask. So to make the measurement, regardless of what industry, what material, what sector of research that you're in, you need to have 3 different pieces of instrument. So starting from LCR meters to impedance analyzer to handheld product or PXI, IF milliwave network analyzer. So these instruments to stimulate electric field, basically energy to your material and get the interact with that particular material so that way we can collect the data. To do that, it requires variety of sample holder or fixture. So these all depends on your material that you are working on. In many cases, many of you, if healthcare or bioengineering, maybe probe is more appropriate, which is the focus on this webinar here. In addition to these 2 items, you need somewhat software to allow you to take the data and then calculate the permittivity value for you. Many of the material research people are not familiar with how network analyzer works or the LCR meter. So the software will come with some easy user interface for you to use, so that way you don't have to worry about the setting of the instruments. So Keysight has this N1500A software that control many different type of instruments, including these instruments particularly go up to 120 gigahertz. And of course, it depends on the frequency of interest of your research. And so you need to choose appropriate instrument. We also have new USB streamline, we call it level analyzer, which is really small that can go anywhere, you know, weighs less than maybe 10 kilograms. We have five different measurement methods as listed here: transmission line and free space, arc refractive, resonant cavity, coaxial probe, which is probably more appropriate for bioengineering. And then the last two is called parallel plate method. So how are all these five different measurement methods mapped out based on what you are trying to characterize or measure? So in this table, on the top it shows the frequency. On the left vertical shows the loss tangent or the DF value, or the imaginary part of your permittivity in relative to the real part or loss tangent. So the lower number is better absorbed, meaning that you have less energy loss. So in your particular application, it will depends. And for automotive or electronics, let's say you want as low as possible, so that way you don't lose energy. Okay. So let's say up to 1 gigahertz. So the parallel plate using the inductance and capacitance method measure those can use these depends on a fixture at higher frequency. Let's say coaxial probe use up to, let's say, 50 gigahertz down to 200 megahertz or so. And then the transmission line method using, let's say 1 gigahertz to 50 gigahertz. The reason for this is the fixture using waveguide medium so that the aperture could be too small in high frequency. And then high frequency because the transmission line not available based on the fixture because the sample could be difficult to fabricate. So we use free space also is corrugate. So each of these I'll go into a little bit more details a little bit later. And so last but not least, the resonant cavity method. So again, this is really good for really, really low loss material, especially for 5G type of material characterization. Okay. In terms of fixtures that we're offering, so for the low frequency, we have different type of fixture as shown here. And then at middle frequency, dielectric probe, high frequency, and really high frequency. In this case, we go up to about 1.1 terahertz, so which is really, really high frequency. And then, so what you have to do is based on what you are researching, based on your material, you have to select the most suitable method for your device. So in this case, if liquid, then maybe you choose the probe, which I'll go into more details. So with that, I'm going to start to cover each individual measurement method and give you some benefits and some limitations. Okay. So for low frequency, 1 gigahertz, there are two types of measurement. One we call a measurement capacitance, and another called measure inductance. So if you're not familiar with the electronic term for bioengineering, that's okay. So there are two measurement methods. So look closely to this particular one. So this is the called electrode, or or you can call a probe. So the sample will sandwich into two electrodes, and the sample can be solid or can be liquid, depends on what fixture that we are using or you are using. And this is the circuit model of the fixture. So we measure capacitance and measure the G. From this formula, we can calculate the actual permittivity value. And this particular solution is work up to 30 megahertz. So because the fixture here depends on the physical dimension of the fixture, and to measure accurate capacitance, in this case up to 30 megahertz. Before any measurement being made, it requires some kind of calibration, and our software will control the instrument, in this case LCI meter. So that gives you a step-by-step instructions. Okay, so this fixture comes with 4 different measurement probe. So it depends on your sample thickness or your sample size. So you choose the most appropriate fixture for your materials. We also give you a range of where the measurement is possible, because this is measure capacitance. So the black solid line is where the measurement accurately measure. So if you outside this black solid line, then your measurement is not accurate. So as example, the blue trace, the equivalent capacitance is 100 picofarads. So, and the relative permittivity is 10, sample thickness is 1 millimeter. So at low frequency, you can see here from 40 hertz to around roughly 200 hertz or so, that is outside the range. So which means that this is not usable result. So you have to adjust your sample to be thinner in this case to bring this down, so you can measure smaller capacitance. I mean bigger capacitance. Okay. So another one is up to 1 gigahertz. So similar, basically exactly the same measurement method, but use different fixture. The sample, basically, this fixture have the spring load here. You can pull it up and put sample between those two electrodes, lower and upper electrode. Yeah. And the sample, of course, you have either rectangular or circular, and you can measure the sample thickness and the electrode bar top and bottom, something like this. And then again, this graph shows you where the measurement that need to be measured. The red line is where the area that need to be measured. And then, as example, I previously said, the yellow one is where your permittivity is 7.5. The thickness is 0.5 millimeter. You can see that this area here at 1 megahertz, close to where the limitation. So which means that your measurement may not be as accurate. So you need to adjust your sample thickness the same as previous fixtures. So to summarize these parallel plate, so basically this is limited by the frequency of the fixture, but it gives you a relatively simple computation that our software can provide for you and control the instrument and work well within sheet. Okay, and also this is not so expensive, but relatively speaking, of course. Okay. Any questions? Just let me know. Next one is transmission line method. So the transmission line method require using network analyzer, which is require the S parameter. If you're not familiar with S parameter, don't worry about it, basically we need to know the actual characteristic of your device. Okay, so the sample holder in this case waveguide, which is a rectangular tube. So sample needs to be fit inside. So it looks like this. The signal will go through. It's called S21, and when signal hit your sample, reflected back with S11, and the same when signal opposite. Of course, the many routes that go through this here. Another one called coaxial. Coaxial is basically is like a pipe, a circular pipe with center conductor. So you can sample your sample to fit inside this coaxial airline, we call it. So in this particular case, there is a center conductor. So you have to drill the hole in the center to get sample to fit. The material assumption here, your sample has to be flat, okay, and no air gap. So the air gap give you an error in the measurement because it's not truly represent your material. And your material needs to be homogeneous. Okay. So this method is broadband from low frequency to high frequency, limited by the actual physical of the waveguide. If it's too low, your sample, because waveguide low frequency, the waveguide is really large, so you may not have large sample to fit inside. Okay. So because the transmission line, there are many measurement models that actually available. Nicholson-Ross model, the NIST or precision model, the transverse model. Each model, as you can see, using some of this model, let's say this one here, using only 2 S parameters. Since it's using only 2 S parameters, it cannot measure the magnetic materials. The magnetic material, permeability, or mu, require all 4 S parameters. Okay? And this is the example of how your sample can sit inside a fixture or the waveguide. So this, let's say this is sample. If your sample is too thin, then you could have a material that support on left and right side and left side. So you mustn't know this sample thickness and its permittivity value, so we can subtract out any of these 2 additional materials that give you the actual result of your sample. So the actual looks something like this instrument. So this is a 7 millimeter airline. This is the actual X band, 8.4 to 12.8.2 to 12.4 gigahertz. We do have higher frequency as well. In this case, this fixture, 60 to 90 gigahertz, it fit well into automotive radar application. And it sample, basically you open up this here, slide the sample in. This fixture here is 300 to 500 gigahertz. Okay. This is really high frequency. So in your case, you may not use as high a frequency. Another one is a free space method. So free space method is non-contact method. So in this case, this is your sample, and this is basically the signal wave that your sample needs to be wide enough to make sure you cover the whole plane of the signal. So how it works is exactly the same as transmission line, except this is over the air. So requires some sample thickness as well. They have some minimum thickness of 1/16 of the wavelength, and the thickness it depends on your actual permittivity value. And this is required 2 antennas, and beam the spot antenna could be work better. In that case, you don't require that large sample size. So it looks something like this. Of course, before measurement, you need to make calibration. So calibration will happen. Uh, this is the measurement plane. So calibration also at this point. I won't go into detail how to calibrate, but our software will walk you through. So this is a example of fixture depending on the frequency band. So in this picture, it shows a focus beam antenna. So this lens here reshape the beam of the signal instead of the full plane wave is focus beam on center. As the low frequency, the antenna is larger, and at high frequency, antenna is smaller. Also, we have a fixture here with micrometer so that help you during the calibration in terms of using the TRL calibration. So you're not familiar with that, don't worry. Keysight Never Analyzer have a step-by-step calibration wizard that walk you through step-by-step and tell you what to do. So this is a super high frequency. In this case, as you can see, using different type of fixture, this is called a quasi-optical table, and it comes with different mirrors, depends on the frequency. In this case, you don't see antenna because it connects somewhere here, so really, really close to another module. The white portion is your sample holder. The actual beam actually maybe around center here. So this is using a fixture that share with other setup. So this is the quasi-optical table, 175 to 110 gigahertz. So the same previous picture, basically signal going through this focus beam antenna, and then go through the sample, in this case metal plate, and drawing the signal through here. Use metal plate also used for the calibration as well. So calibration, there are two types, one tier and two tier calibration. And again, the software will walk you through. So if I compare this measurement method compared to the method that I have not covered yet, so basically transmission line free space is broadband, okay, but it doesn't have enough measurement resolution. Some calibration is required, and again, this is broadband. So other method, resonant cavity, which I will cover next, I believe, and then I'll go into more details, which just give you a really good low loss measurement, especially for 5G or people who want to measure really low loss material. There is the industry they call International Electronic Measurement Initiative for 5G. They're looking to come to standardize the material sample as well as measurement method, which I part of the team to come up with that type of process. And we're supposed to publish the paper and do our finding in about a year or so. Okay. So the resonant cavity method. So the cavity method, basically, this is one of the fixture that Keysight provide, and this is the TM, this number. So which is a standard that used to design to this fixture, and sometimes the material in particular that you need to measure require certain standards. Okay? So the basic concept of this measurement in this particular method does not require any type of calibration, okay, which is much more easier compared to the transmission line and the free space, because those two methods require a calibration, which in some cases require additional hardware like calibration kit. Okay. The parallel plate method I covered earlier for the low frequency also require calibration, but you don't need additional standard, or the fixtures come with the standard and a metal plate to use for the calibration, and the software will walk you through. So in this particular method, since this not require calibration, it's a lot easier to use. However, this method is only give you a one single frequency. Basically, it measures the empty fixture, it measures the resonant frequency of the fixture, and measure the Q value or the bandwidth. The higher Q value meaning that the narrow bandwidth that gives you more precise measurement in terms of the imaginary part of your permittivity. Okay? When you put the sample in, the frequency resonance shift as well as your bandwidth change. The amount of change in the bandwidth or the Q that give you the imaginary part of your permittivity. In change in the frequency, it gives you the real part of your relative permittivity value. We have a different type, different frequency of the fixture. So this particular one we call the split pulse dielectric resonator from 1.1 to 15 gigahertz. Of course, require additional software, which is our software I mentioned earlier. And this one here basically aim for more higher frequency or millimeter wave frequency, especially 5G FR2 is starting about 28 gigahertz. Some of the 5G frequency using FR1, which is sub 6 gigahertz, below 6 gigahertz, so it can use one of these fixtures. And of course, the automotive radar at 77 or 80 gigahertz, so you have to choose one of these fixtures. In addition, we call it balanced circular disc resonator. So this particular one, the fixture looks something like this, and this is give you a few different resonant frequencies. The resonant frequency will depends on your sample thickness and also depends on your real part of your permittivity value. If you resonate, let's say at 20 gigahertz, and then if you take its harmonic of that to get to 40, 60, 80, and 100 gigahertz, so give you a few measurement frequency points as compared to this one, only one frequency points. Okay. So based on that, so which fixture should you use? Again, this is based on the loss tangent value or the imaginary part of your permittivity. So, so this balanced resonator gives you actually can measure lower as well, much lower loss tangent value, and this here also give you somewhat equivalent to about of this fixture, but give you only single frequency. So we have other methods that are available as well, and some of these methods that's commercially available, not from Keysight. So from Keysight point of view, we have this fixture, these fixtures. Okay. So now, because because your material can be isotropic or non-isotropic, so you have to be careful how you choose which resonator to use, and you have to also understand that how your material behave, and also sometimes depends on what standard that the particular material is required to measure under. Okay. So back to this slide, remember I said I will answer why is a different result. So the different result because they use different measurement method. Okay, so material structure behave differently depends on which way that material is being used or the signals is applied. So in this case, they're using basically we call in plane, out of plane. So X, Y, X and Y is called in plane method. So the Z or the vertical is out of plane method. So that's the term that official term that they use. So in this particular supplier B is using the out of plane method. So if I go back to this slide, so which method actually uh, uh, provide or which fixture actually provide our plane measurement method. So in this case, the balanced circular disc resonator provide our plane method, or the using the this fixture, or this is ring line resonator. So the other method, this other method here is only for the in-plane method. Okay, and the another method that I did not mention is this method here, peripheral open resonator, and this is uh, basically using open waveguide with a mirror to act like open resonator, available from our solution partner Keycom. Okay, so that comes to the summary of that particular cavity method. So this is absolutely the best for the low loss and very sensitive to low loss material. This is only a method that require that must use for people who need a super accurate low loss material characterization in the high frequency like millimeter wave 5G automated radar application. Okay. So let's talk more specifically close to the bioengineering. I hope this is the Dielectric Probe. So Dielectric Probe can use with the benchtop instrument or the Firefox handheld product or USB Streamline V and A never analyzer. In this case, require PC to run this instrument. So the typical setup, the software can run inside the network analyzer, and it has a cable connect to the port, can be either port 1 or port 2, and submerge into liquid, soft, like phantom material, or it can be even solid material, as long as your sample is flat. I've seen some of the university in Australia using probe to measure some human skin and scalp too, which is interesting. So I think you are bioengineering. You probably know how to handle those type of sample. I'm not, so I have seen how they use. So how it works? It works is basically based on S parameter S11. In this case, we send the signal down to the probe, and we measure reflect off the material, which means that your material need to be effectively um, infinite thickness. However, if your sample is thin, so perhaps you can stack up your sample, or you can put some sort of absorber material underneath so that you don't measure from the bottom. So the idea is you want to get the reflection from your material, not from the fixtures. So also, and this is only applied to isotropic material, and make sure there's no air gap or bubble. Okay. So again, before they make the measurement, we require calibration. The calibration is really simple. The calibration standard, so you can be air, okay, like an open air, short, which is come with the dielectric probe kit, and water. Water needs to be distilled water, so that way we know water, as you know, is well known characteristic, so we know what it is, and even at a different temperature, we can put in the temperature as well. Or if you have a load, you can use as well. So calibration definition can be anything like something this parameter. If you want to use your own standard, you can put it in. So the probe itself, we have, I show 3 different probes here. So one is the stop at 20 gigahertz, and the other 2 at 50 gigahertz. I also show you the actual dimension, so that way, you know, give you an idea of how big it is. And then this particular one, especially for food, health, research, or bioengineering. So I highly recommend this particular one. It gives you a more detail of the type of materials made of. Also, this is hermetically sealed on both sides, so that way the moisture does not go in, and also can be, you know, autoclave and can be sterilized, so that can clean really easily, especially for the health research, so you can sterilize these probe. So the other 2, because we don't seal on this side, so the moisture could go inside. Okay. So one of the good thing about this particular probe is smaller tip. So that means that your sample can be small, especially, you know, bio or health tissues, or human tissues, or things like that. That sample could be small. In addition to that, this particular probe, you can actually submerge into some kind of material that you can leave it there. So for you know, in case you damage. So when you order this probe, it comes with 3. So these are the calibration standard. This is the short standard, short standard, short standard. So this particular probe, since the gold piece here made contact with the probe, it may not give you good contact. So we highly recommend to insert this conductive disc into here when you do the calibration. Okay. So this is one of the measurement example that we use, sample A and sample B. So the sample B, I believe, is the purple color, which has more water. So it's the real part permittivity is much higher because contain more water. The other one, the B sample, so you have less water, maybe have some additional other material, so less water, so permittivity is lower. This is the real part of permittivity, and this is the imaginary part of permittivity. As you can see here on the water, okay, so you can see here at the low frequency, 500 megahertz, the real part starts small. As frequency increase, it keep increases because the molecule rotate faster as the frequency apply. At the peak, that's where the relaxation time happen, or the time for this particular material to go back to original state. So the measurement is really sensitive and have really high sensitivity. We can actually correlate between, you know, the 80% water or 20% of other material. You actually track it really well. We can actually plot how sensitive into the actual mix of your sample. Another study is done by University of Washington. This is in the process and process control and analysis. So in this case, we have 2 different test setup. One is 10% water, I mean 10% sugar and 90% water. So the idea is you want to identify different type of sugar. Okay, so sugar is 10%, water is 90%. Another one we did is we show we did 10%, 1% sugar and 99% water, and both can we measure. We can tell the grouping of the sugar. In this particular plot, it shows the 10% sugar and 90% water. Interestingly, that in the real part of permittivity, you don't see change as much. But if you look at the imaginary part of permittivity, which is the lost energy part of the permittivity, you can see clearly a big difference. If you expand it out, you can see the difference. Okay, so with that difference in the imaginary part, and so they use some software, Chemo software. I think for chemistry background, know this software. Basically, this software use processing and the analytic of taking this content and correlate between different results. So they actually measure it many times, and you can clearly identify which group belong to which sugar. Okay? So, and this is the 1%. Even though some of these are closer to each other, you know, they still clearly tell which group of sugar it belongs to. And then another study, this is carbon nanotube. Okay, so in this case, it's all set up using the network analyzer. Nowadays, you can use a USB VNA, smaller, or Firefox sitting here. So you don't have to worry about the big thing here. So this is a tub that have some kind of continuous stirring, so that way the nanotube is continually mixed. And there are two types of nanotube, one with a layer, another one with two layers. So with that, note here we use the electronic calibration module. What this electronic calibration module does is when you do the calibration, these connect into part of your setup. You do open, short, you do calibration here using open, short, and water, or any type of standard that you have. And then you submerge this into your material and then continue testing, you know, days, weeks, or whatever. And to you can use this any change in this instrument or cable change. This electronic eCal can correct for any drift into the setup. So that way you go back to original calibration state. This will be continual process of measurement. This is really helpful for over time of measurement. And using the same software, they can clearly correlate between two different nanotube layer, 1 and 2 layers. Okay. Another example, I think I borrowed this from this particular website, courtesy of this article, and actually using the dielectric property to identify different type of meat, which is pork, chicken, and beef. So clearly the conclusion is that this work indicates highly promising initial result of discriminating different type of meat and the species of origin. Okay, so also it says that promises clear, distinctive result. Okay? So due to its simplicity, this technique can be utilized as support initial screening before proceeding to detailed analysis using other time-consuming method. So it's clearly that using the dielectric property is a way to quickly identify certain type of materials. Okay. So this is graph of different of, of beef, chicken, and pork, and you can see the pork is quite different from the beef and chicken, which is maybe that's why the pork require much more higher temperature, longer time to cook to kill some of the perhaps that come with the pork, and the purple is the mix of the meat. So you can see still the pork is clearly show even in mix batches. So this is the real pork. This is imaginary pork. Okay, and they do the same study. In this case, this materials are being sterilized, so meaning dry, air dry, or something like that. So you still see the pork is still obviously show the, the difference between the chicken and the beef. Also, it shows off, it show on also the real part of the, I mean, imaginary part of the permittivity. Okay. So in summary, so the probe is actually open-end coaxial probe is useful for permittivity variety of liquid and soft solid. Okay, it can also be used to correlate property of interest, and it can cover from 200 to 20 or 500 to 50 gigahertz. It is more acceptable for solid flat, if you can get that flat enough, so you can actually measure the flat sample as well. Okay. So next in the research area, so for 5G FR2, let's say 40 gigahertz. So basically, it require in different types of material, and it require lower loss material. So we need to make sure that we provide the appropriate and using the correct method and fixture to measure your material. Okay. So the key is that any type of material, especially in electronics, that the ideal performance is like air, right? It's like nothing there, even though there are some material there, but you want to make it like nothing there. So that way you don't lose any energy, or you don't have any effect by putting additional material. For example, here, lower DF, I mean DK and DF, lower DK or lower dielectric constant or permittivity, the real part of permittivity, to achieve lower latency or delay in signal. So when you have lower loss, it means you avoid signal loss at high speed of the signal, meaning that you don't waste energy. So, so the user requests are both basically a target above 30 kHz for 5G. And some other example here of the materials that are available. This is the permittivity, and this is the propagation delay. Okay. So again, the aim for this type of people is low loss. Okay. So you have to use appropriate method, and this is the plot here is a DK, and this is DF. So the other area is biomedical application. So there are a lot of research in breast cancer detection. Okay. So as you know, the current breast testing for cancer is quite, I would say, painful. I would not know that because I'm not female. And also a microwave sensing as well. And then the phantom experiment, some digital processing, okay. More other area that research doing, cardio type, okay. And also some of the phantom examples here, digital processing. Um, And then also testing, researching under stroke or brain injury, okay, and also because sensing and phantom, and again, so there are variety way of process that over the years that do some research. The other way, other research into, as you can see, these millimeter wave scanner, you see that in the airport, also oil and gas. We want to make sure when, especially the oil industry, they want to detect any production that affected by maybe too much water, perhaps. So they want to stop the production so that the way they don't waste too much time. And then some of the moisture measurement, let's say for medical industry, you want to measure the moisture content in the medicine, in the pill, so that way make sure you have enough moisture or just enough so that the pill doesn't uh, erode over time. Also, food processing could be another also research area because food processing and safety is become more and more critical nowadays. So I think using dielectric probe could be a, a ultimate solution that can do really fast indication of if anything changed. Our software can also set up so that measurement over time as well as increment of measurement. Okay, so some of the solution that we have. Um, we already talk about 5G using resonant cavity method. I already talked, so I wouldn't say too much in there. The probe, for human safety and testing, I think the probe is probably the best tool available, especially for measure liquid. Um, Using smaller probe, slim probe may be better because it doesn't require that much sample. And then some other one for phantom experiment, some other solution that we have using really fast network analyzer and over time. And this is a clinical trial now, some of the example um, from this type of setup to this type of setup. So to make some progress. So the success story. So okay. So again, some of this early on stage of the prototype, and now become something like this, which is from this company, and Keysight also involved with some using our instrument. Okay. Brain imaging, as you can see earlier, and now that over the years it become instead of from here to smaller and now become more wearable. So this is where research area and making progress, and also using some of our Keysight products. Okay. So, and this area here is University of Queensland, and these are some of the professor, researcher, and using many types of antenna here, and using maybe perhaps different type of instrument. Now we are using these different PXI VNA that can provide multi-port measures simultaneously, and these actually can detect a small items in the phantom, so that you actually see clearly the actual foreign object in the phantom material, so that we can detect perhaps maybe cancer or tumor. Yeah. Again, this is the same thing that I showed earlier. So some of the success story for food safety using dielectric probe is a good way, early indication of before you spend a lot of time using more detailed analysis. So where to get help? This is the website. To go to our website link, so you can lots of information there. So with that, I believe I conclude my live presentation. I hope that was useful. It takes a little bit about an hour, a little bit over an hour or so, and I went a little bit fast. And now I open up to a live discussion. Thank you.
You Sai, that's very interesting.
Thank you.
Thank you,
Sai,
Sai.
Yes.
we do have a question coming in from Johannes, and the question is posted under the Q&A tab.
Okay. So should I stop sharing? Stop sharing.
Yeah.
Let me go to chat. Okay, so the first question, measuring sugar content, different type of sugar is really important for food safety.
No, that's not the
okay.
question. The question
Okay.
is down there under the Q&A tab. That's the chat that I posted up. Sorry.
So I don't see.
You don't see the question? Okay.
No.
Okay, let me read the question. The question goes like this. The last question, which is measurement method that fit for measuring a solid plate sample in rectangular or circular form for a broadband frequency about 500 megahertz to 1 gigahertz question mark. And what measurement setup that is required for my measurement?
So the frequency 500, or I see, because 500 megahertz to 1 gigahertz, and the sample is well,
Rectangular,
rectangular. Yeah. So so when you say broadband 500 megahertz to 1 gigahertz, to me it's not broadband, but anyway, let me. So let me go back to my slide on my own here. You don't have to see. So yeah, let me go to first. So share my screen. So if your sample is rectangular, so this fixture, so this fixture, it the measurement point for 1 gigahertz. So so this one, it would be appropriate for your, regardless of your sample is rectangular or or circular, right? Or circle. So this is basically it touch the thickness. So this touch the thickness of the sample is sandwiched the two. So as long as it fit inside, as long as thin enough to fit inside here, then you can measure up to 1 gigahertz. So that would be the fixture. Yeah, can you hear me?
Yes, I can hear.
Yeah, okay.
Yeah, I think this fixture, the model number that you mentioned is 16453A.
Correct. Yeah. Yeah. I think there was question coming from Indonesia, measure, I don't remember exact details, but it was up to only 20 megahertz. So I recommend these fixtures. This fixture up to 30 megahertz. If you want to go to 1 gigahertz, this is only fixtures available.
Yeah, let me send the link from Keysight so everybody can see the fixtures. Yep. I just post up the link to Keysight where you can read the material, the content. right? It's from 1 megahertz to 1 gigahertz.
Right. So is there any other questions on the chat? Can you see?
Yeah, hello. Sai, this one follow up question by Pak Johannes. So can I use two pieces of conventional waveguide plane WR137 plane as a sample holder to measure a material which is connected to VNA?
Your voice is choppy. Can you?
Is it?
Okay, I'll repeat for it. So this is a follow-up question from this earlier question by Johannes. So Johannes is asking, can I use a two-piece or conventional waveguide flange, waveguide WR137 flange as a sample holder to measure a material which is connected to VNA?
So you want to measure, you want to take the sample and sandwich into it between two waveguide, or you want
waveguide,
yeah. So you want to fit inside the waveguide, or you want to waveguide to sandwich the two without going inside the waveguide. Are you following me?
Yeah, maybe can you explain the both method inside the waveguide and outside the waveguide? How does this work?
Okay. So if you can fit your sample inside a waveguide, and if you have your thickness equal to a quarter wavelength or half wavelength, then definitely you can use waveguide. If your sample cannot fit inside the two waveguide, then you put the waveguide in between. You put the sample in the between two waveguide, then you tie it together. Use like a sandwich, right? But your sample actually not inside the waveguide. In that case, uh, because waveguide have uh, dispersion, and your S parameter will not be accurate. So it will give you wrong answer. If you can live with some grossly error in the measurement, then that will work. But I cannot quantify the error because the waveguide is dispersed. That's why we want the sample to fit inside the waveguide, so it captures so no waveguide dispersion. If your sample is powder, I think maybe you're better off pack it really tight, and then using the probe to, to, to submerge inside your powder. So that way you eliminate the air gap. So that way you can have better measurement. But using the dielectric probe, it does not give you the magnetic property. Does that make sense?
Yeah. Okay, I think yeah, Johannes did mention is sandwiched between the waveguide. So yeah, Johannes, you can continue to ask furthermore. We have a lot of time. Another question coming from Caesar Kunia. Oh, okay. This is an easy one. He said, "Dear all, my customer from University of Indonesia would like to try N1500 air trial license. Is it possible to request a trial license?"
Yes, currently on our website, the material support website, you can get 30 days trial license. If you use your PC, it gives you 30 days. You could also use your friend's PC, you get another 30 days.
Yeah. Let me give you the link here. Okay, I'll press up the link on top of the chat so all of you can see. Go to the link, and then once you enter the link, there's a tab in between the website. It's under the trial and licenses. So all you need to do is just apply for the trial license, enter some details, and you get the software.
Okay. Hello, Sai. This one,
Yes.
I have the question from Pak Taufik to me. They asked regarding the slide that you presented by today. Can you send the presentation slide to me, to us, so I can give to Pak Taufik regarding the presentation slide?
Sure. Yes.
Okay.
Yes, I can do that after this.
Is there any other question? Tapi Pak Yohanes Galih, mungkin ada pertanyaan lanjutan Pak Yohanes Galih. Pak Sesa, atau Pak Sigit.
No, I'm okay, Pak Ria.
In next few months, Keysight University try to promote many of the Keysight solutions. So I'm going to do some video recording regarding to 5G millimeter wave video, and also have some demo actually taking picture of measurement setup. And then after that, I'll going to continue with, let's say, dielectric probe, starting from scratch. From when you're receiving your dielectric probe kit, how to assemble it, how to make connection like this, how to install software, how to do the calibration, measurement, and few tips on how to use in the software, general report, things like that. So I will make complete video for each of the measurement method, and perhaps maybe all of these different fixtures so you can see how the process works.
Okay, Sai. This one, another question from Pak Yohanes Galih. Said that they just use the trial version of the N1500A software, and there is an air gap correction feature. Is it able to eliminate the dispersion that you already mentioned before?
No. So that air gap, actually, I think, let me do something. I think we have lots of time, right?
Yes.
So let me actually show what that is for let me bring up the software here.
Yeah, maybe you can share your software and share the screen how to do the measurement.
Yeah.
I think that'll be very helpful to
So let me.
Your Highness.
Okay. So let me give me this. So you see my screen?
Yes.
Okay, so I don't think I can make it bigger. So right now I don't have the instrument connected. So let me go to start transmission line method. So I want to cancel because I work from home. I don't have instrument. So go to measurement, define measurement. So go to sample holder, de-embed or gap correction.
Can you go a bit slower, Sai? Yeah.
Oh, so go sample thickness, gap correction. So let me go back to sample holder, change this to waveguide. Okay. So gap correction. I just put anything in for now. So that gap correction is for this. So let's say this is your sample, this is your fixture, the green color. Your sample is like not fit the so gap correction is to correct for this gap, not for the dispersion. So that's why gap correction will not work.
Okay.
So if you're doing a measurement, if your material is non-magnetic, I usually suggest not using the first model. Okay, because first model, the software will try to calculate the uh, the epsilon, the permittivity value, and the permeability value. So since there is no permeability, it's going to put one there, but sometimes software has to go back and forth, try to calculate it too, and sometimes give you a wrong answer. So I suggest using like trans-fast model or the reflection transposition model. This way, it only measures the permittivity value. So this transmission line method actually we have different type of we have the administer version and operator mode. So the administer mode, you can do anything you want. And the operator mode, basically, you will change that mode to define and only certain things that can be modified. For example, only sample thickness. So that give let's say, operator um, only know how to make a measurement in case of use in the manufacturing process.
Hello, Sai. Is there any we still waiting for some graphic or others or
Oh, okay.
oh no?
Okay.
Or maybe Pak Yohanes, is this already explain what become your curiosity regarding the eliminate the dispersion in the air gap? Um, because before saya already said that it cannot be done right side to
Oh,
eliminate the air gap
yeah.
connection.
I mean, I think, I mean, I, I, I think I think if you, I mean, you can always try, but I would not recommend it if you want a accurate answer.
Hmm, okay.
Can can you get sample to fit inside the waveguide? Is that too big? Can you cut it?
Sorry. Can you repeat? Sai, what become your question?
So so can they cut sample to fit inside the waveguide?
Are you honest? Is there any more question regarding this one, or maybe respond regarding the question from Sai is apakah bisa memasukkan beberapa sampel untuk di dalamnya antara beberapa itu? Hmm. I think maybe respond from the Pak Yohanes Sai. Maybe if other have any question regarding this topic, or maybe regarding another which is connected with the material measurement, you can also ask in this session.
Looks like from the same person. I can pronounce the name at
Oh yeah,
8:37. Yes, I design a
yes, yes.
sample to fit the waveguide, and I need to measure both mu and epsilon. Yes, I mean, if you can get your sample inside the waveguide, then you can measure the mu and epsilon using the Nicholson-Ross model. The model, the first model on top when you select the define measurement, the software. Yeah, this one. See, the software give you the mu and e, right, epsilon, and that's where, and then also give you a sample thickness suggestions too.
Okay. So it can be done to measure both mu and epsilon using the software. Yeah. Right. Okay. Hello, Sai. Can you hear me?
Ah, yes, go
Oh
ahead.
yeah.
You have question?
Not yet. There is no question more, maybe from the attendee for the participant. Uh, Maybe Daniel, you have something to share? Maybe some.
No, I don't have anything in particular to share. I think the maybe this is I just want to share what my observation is my role in education for Asia Pacific. I see there is a growing trend, or I won't say growing. The demand for material measurement is always there. It is a continuous opportunity for all of us as a researcher, whether you are in R&D or you are doing some sort of development activities. Like for example, what Sai did mention about 5G, automotive radar, all this requires new material to support new applications. Whatever that we have or was designed maybe 5, 10 years ago, it may or it may not work for today's or future application. So material measurement has a lot of demand, has a lot of application. And one of the application that also Sai did highlighted is also according to our topic for today is related to bioengineering or healthcare. So actually Sai did share about how does using dielectric properties technique, measurement technique to detect cancerous cell, to detect tumor, to detect kidney stone or brain stroke. There's also universities from maybe like Malaysia, the place where I come from, and also like the link that I just shared from Canada. They use dielectric properties method as a way for a very fast detection to measure food safety. Because like in Malaysia, we actually uh, look into a lot of halal food export. They want to make sure that the food is not being contaminated by foreign substance. So that is one. The other one is looking into what should I say? Uh, Related to food quality, not only like food safety, but also food quality. So the application of material measurement, whether you are in not only in electronics or RF area, but it is actually for health and food or even agriculture. So that's what I just want to brief up uh, from my observation.
Okay. Okay, thank you, Daniel. Okay, maybe if there is no other question, maybe we can closing for today webinar. Daniel, right? Is it okay?
It's up to you.
Okay.
Yeah, it's up to you. It's up to you.
Okay. Okay. If there is no other question, thank you very much for your participating in this webinar. Hope you all can bring something from the material that we already prepare and share this morning until this noon. And hope to see you in our next business meeting or our next webinar. And if you still have any question regarding the topic or other topic about what Keysight can do, you can always drop an email or contact us in at marketing at berca.co.id, or you also can direct email to me at Rea Romeo Eco Alpha hermawan at berca.co.id. Okay. Thank once again, thank you for all of your participation in today's webinar. Stay safe in this pandemic situation, and bye bye.
Thank you. Bye.
Thank you.
Thank you. Bye-bye. Bye-bye, everyone.
Thank you very much, Daniel, Sai, and
Thank you.
PK.
Thank you, Sai.
Thank you.
Yes, I. Bye-bye.
Bye-bye.